In today's video, we're going to talk about the history of the atom and how the experiments that were done to discover the properties and characteristics and really the structure of an atom. The two things we're going to focus on is how they discovered electrons and then how they discovered the nucleus. You can see there, as far as discovering the electrons, there were two main scientists that were instrumental in that, Thomson and Millikan. And they used something called a cathode ray tube, which I'll show you some videos here in a little bit. And then as far as the discovery of the nucleus, the scientist Rutherford did a lot of that. He used a very classic experiment often referred to as the gold foil experiment, in which through that experiment he was able to understand more about what the nucleus is, its size, and its size relative to the rest of an atom. So what I have here is a couple of videos, links. They can be very useful. What I have is I have these linked actually out on Blackboard, so probably a little bit better if you want to just go to them here. So when you go into chapter 2 or chapter 3, under the web links, under the notes actually, sorry, you're going to find, here's a link to a cathode ray tube experiment, the cathode ray tube and paddle wheel, and two different links to Rutherford's experiment. They give a lot of information, a lot of details relative to that. Those can be very useful, as well as the information that you have in the book. The next thing we want to talk about is, okay, they've discovered these different particles within an atom. Something we call electron, something we call a proton, and something we call a neutron. Now, we're learning now more recently, in the 21st century, about other particles that are smaller than this and how they affect an atom. We're going to sort of leave that alone for right now. We do want to talk about some properties and characteristics of an atom, because this leads into our next set of chemistry calculations as we get into the end of chapter 3 and then the rest of the year. So a couple just things here. If we're measuring the mass of these three different particles, here are some numbers that represent their mass. Kilogram values as well as gram values. Again, numbers you do not have to memorize, but ones we will have to use. Now, if you notice, those numbers are pretty large in terms of scientific notation. Very large negative exponents. So it's kind of was tough to manipulate and use those numbers. So what they did is they basically created another scale that makes it easier to manage those numbers. I use an example of, well, the distance from here to Cleveland is 2,500,752 inches. Number I completely made up, but my point being is, to measure the distance from here to Cleveland in inches doesn't really make sense. So what do we use? We measured in miles. So again, as they started to discover and learn more about the properties of the particles within an atom, they realized, you know what, it doesn't do us any good to talk about kilograms and grams of these particles, because they're so small that we need to have another scale that makes those numbers more manageable. So they created what we call the atomic mass unit. Simple designation, AMUs. Right. So the definition of 1 AMU is 1.660 times 10 to the minus 27 kilograms, or 1.660 times 10 to the minus 24 grams. You will see them published in different places with maybe a few extra digits, maybe in some places with less digits. Now, what's the significance of these? Well, what we can then really say is the mass of one proton, the mass of one neutron, and the mass of one electron are very simple. One proton, instead of saying it has a mass of 1.673 times 10 to the minus 27 kilograms, or 1.673 times 10 to the minus 24 grams, we can say is the mass of one proton is 1 AMU, about 1 AMU. We can also say one neutron has a mass of about 1 AMU. Now, compared to those two, an electron basically has no mass in terms of AMUs. So as we're doing calculations, it's going to be a lot easier to say the masses are 1, 1, and 0 than to be using these numbers. So Here's what I want to do. Let's say we have an atom of carbon. And in this atom of carbon, there are 6 protons, 6 neutrons, and 6 electrons. Now, what I want you to do is to calculate what the mass would be for this carbon atom in kilograms and in grams. Well, what we would do is we would go back and say, all right, well, I got 6 protons, and each proton has a mass of 1.673 times 10 to the minus 27 kilograms. Plus, I've got 6 neutrons that each have a mass of 1.675 times 10 to the minus 27 kilograms. Plus 6 electrons times 9.109 times 10 to the minus 31 kilograms. Well, when we add that all up, we get this huge number, 2.009 times 10 to the minus 26 kilograms, or 2.009 times 10 to the minus 23 grams. Now imagine if we had these numbers on a periodic table. What's the mass of carbon? 2.009 times 10 to the minus 26 kilograms, or 10 to the minus 23 grams. Doesn't make any sense to try and have numbers like that when we can create a scale that makes it more manageable. Now, to approximate, if you remember what we said on the previous screen, that 1 proton is about 1 AMU. So we have 6 protons, 6 AMUs. We have 1 neutron is about 1 AMU. And 1 electron is essentially 0. So if we got 6 protons, 6 neutrons, and 6 electrons, we have an approximate mass of 12. It's a lot easier to say the mass of a carbon atom is 12 AMUs than to say it's either one of these. Now, to be more specific though, we do want to calculate this in terms of AMUs. So on the previous screen we had this value. 1 AMU is equal to 1.660 times 10 to the minus 27 kilograms. Well, guess what? Here is our first official chemistry conversion factor. This relates kilograms to AMUs. So if we go to calculate this, we would say, all right, if we want to calculate how many AMUs do we have here? Here's our simple calculation. We have 2.009 times 10 to the minus 26 kilograms times, we write this proportion in a fraction form so that we can get rid of kilograms and solve for AMUs. So 1 AMU goes on the top, 1.660 times 10 to the minus 27 kilograms goes on the denominator. Kilograms cancel, and we get an answer. So what I want you to do is to get your calculator out, actually do this calculation, punch in scientific notation, and I'm going to just pause here for a second to give you a chance to work that out, and we'll kind of talk about rounding and all that stuff. When you do this calculation, you're going to get an answer of 12.1024, and the digits keep going on and on and on. Well, here's what's kind of nice. This is the number we put on the periodic table. The mass of a carbon atom is 12 AMUs, not 2.009 times 10 to the minus 26 kilograms or 10 to the minus 23rd grams. Now, there's a lot more to this, but this is kind of where we want to start with in our conversation. So what I'm going to have you do is one more example here. So in this example, what you have is a sodium atom. And in this sodium atom, there are 11 protons, there are 11 electrons, there are 12 neutrons. And what I want you to solve for is, what is the mass of a sodium atom in kilograms? What is the mass of a sodium atom in grams? And what is the mass of a sodium atom in AMUs? Now you will have to refer back to the previous screen. We just jump back there. That has the conversion factors for one electron, one proton, and one neutron, plus the conversion factor for converting AMUs to kilograms and grams. So what I'll have you do is pause this. I want you to work on solving for what one atom of sodium would be in terms of these three values, and we'll come back and talk about them. Okay, now that you've spent all that time and done that calculation, here's what we're going to do. We're going to look at these answers in class. So at some point, what I want you to do is ask me to look at what you did for this calculation, and after I've done that, then I kind of have then I'll know that you've watched the video and you're working through these calculations, and if something's not quite right, we can talk about it. If you're good to go, then you just move on. Alright, the last little thing here we're going to talk about in this section is just the size of the atoms. So the size of an element is very, very small of an atom of an element. And be on the range of 40 picometers up to 270 picometers. Now, just to give you sort of some perspective, 1 picometer is equal to 1 times 10 to the minus 10th centimeters. Another way to say that is if we have 1 centimeter of space, okay, the distance, okay, of 1 centimeter, there's actually 10 billion picometers in that space. Imagine you have a distance of 1 millimeter, okay, one sliver. There are 1 billion picometers within 1 millimeter. So we have atoms that are on the range of 40 to 270 picometers, and there's a billion of them in a millimeter space, or 10 billion picometers in 1 centimeter space. So bottom line, number one, they have very little mass, because we saw that in our examples as far as protons, electrons, and neutrons. And number two, they're very, very small. Alright, so that kind of finishes up the just beginning to talk about the properties and characteristics of an atom, and we're going to lead into more calculations and measurements dealing with atoms as we look at very specific elements.